In this video I'm going to talk a bit about how we use Runge-Kutta methods for solving systems of ODEs. Okay, so just to define a system of ODEs, remember that any ODE which we solve using Runge-Kutta methods has to be a first order ODE, so we have to rewrite higher order ODEs as a system of first order. So here we've got n first order ODEs. So on the left we've got y1 dash, y2 dash, all the way down to yn. So we've got n equations, and on the right hand side we've got our ODE functions. Now these functions, we have t, which is our single independent variable, and we have y1, y2 up to yn, which is our functions of t. Okay, so what we can do is, if we use in vector notation, if we let the vector y be y1, or the vector of y1, y2 all the way down to yn, like that, and we define a vector f, which is a vector of functions, so with f1, f2 all the way down to fn. Now each of these functions is a function of the independent variable t and that vector y, which is just defined. So doing that, you can rewrite a system using vector notation as so, like we have here. So we can easily rewrite our Runge-Kutta methods for solving systems of ODEs by, if we'll have our vector y, so we'll have our new values of either vector y equals current values of vector y, multiplied by the same sum as for a single equation case, but here we've got a vector k, which is a vector of intermediate stage values. Now k, for each equation in our system, we're going to have a separate value for each stage in our method. Okay, so here's our vector k. So this is calculated using the vector f, which is a vector of functions. Okay, so to calculate the stage values for each equation in our system, we're going to have a number, i.e. s, individual stage values. So what we're going to do is we're going to define a matrix K, which is s by n. So this matrix K has s rows, so each row corresponds to an equation in our system, and each row corresponds to a stage in our method, and each column corresponds to an equation in our system. Okay, so what we can do is we can rewrite our stage value calculation using matrix multiplication. So here is our standard stage value calculation with the summation expanded out. Okay, so what change we're going to make here is we're going to rewrite this bracket. So I could just try and highlight it. I'm going to rewrite that bracket as a matrix multiplication. So if we have our ith row of A, of the matrix A, that's multiplied by this column vector here, and of course, so you have ai1 times k1, ai2 times k2, etc. So that summation there can be written as the product of these two matrices. Now this matrix we've defined up here to be the matrix K, and here we have the ith row of A, and so we define it using this notation. So A in square bracket subscript I star just denotes the ith row of ith row of A. So our function calculation is simply yn plus h times that row, ith row of A, times the k matrix. Okay, so once the stage values have been calculated for an implicit Runge-Kutta method, that's quite straightforward. We now have the updating of our vector yn plus 1, and so if we expand out the summation, so we have b1 times the vector k1 plus b2 times the vector k2, etc. Or we can rewrite this summation here as the transpose of our b vector multiplied by our k matrix. I should say, but the vector b is assumed to be an S by 1 column vector of b values. So it's much more simpler if our stage values are in matrix form, i.e. this matrix K, which I'll just go back a slide, is defined here. Okay. So this results in this following algorithm, which is how we solve a system of ODEs using an explicit Runge-Kutta method with adaptive step size control. So if we're presented with an initial value problem of this form, so notice this is a system of ODEs, we have some domain, t goes from a to b, and we have an initial value of y. We're given an initial step length of h. Now remember, that's going to change, so for the first step we're going to use h, and all subsequent steps that will change slightly. And we're going to have an accuracy tolerance of toll, so that's something that we could also set. So to start with, we initialize our initial value of t to be the lower bound for our domain. We initialize our initial vector y0 as the initial vector ya, and set a counter to be 0. Okay. And we define our embedded Runge-Kutta parameters. So this will be some matrix A, vectors b, b star, and c. Okay, so if we were to use, for example, that's on a different video, but if we were to use butcher tablet, a cash carp, or a Thalberg, or a Dorman Prince, that's where we get our values of A, B, B star, and C from. Okay, now we need a loop. Now ordinarily, up until now, we've probably used a for loop because we'd have a constant value of the step length h, and we'd know in advance how many steps we require. But because we're changing h after each step, we have no way of knowing in advance how many steps, so therefore we have to use a while loop. So we're going to loop until our t value is less than b, which is the upper bound of the domain. And the first thing we need to do is calculate our k values. So I'm going to initialize our k matrix, and remember this is an S by n, where n, big N, is the number of equations in our system. I'm going to initialize that to be 0. And then we loop through each row of k. So from I goes from 1 to S, where S is the number of stages, and we calculate our function, okay, using this matrix multiplication here. Once we've done that, we calculate the estimate of our error. Okay, so this is k transpose multiplied by the vector b minus the vector b star. So this is a matrix multiplication. Okay, so that will give you a vector. We take the absolute value of each number in that vector. Oh, sorry, this will give you a single value. Then we take the absolute value. Sorry, I'll say that again. So this matrix multiplication here, this will give you a vector. Okay, we take the absolute values of the vector, and then we take the maximum one. Okay, so this is kind of like the worst case scenario. So for all of our equations in our system, we're taking the worst. We're taking the one with the largest value, and multiply that by h, and that gives us an estimate of the error. Then we compare our estimate of the error to tolerance. If it's less than, okay, we can advance the solution. So we advance the solution using our Runge-Kutta method. Note that this is the matrix multiplication. We update our t value, and we update our loop counter. Now, unlike the step doubling, whether our step was successful or whether it wasn't, we still change the step length h. And so using est, which is our estimate of our error, we calculate the ratio at which the step length is going to change by, and then we change our step length by simply multiplying the current step length by the ratio. Okay, once all that is done, we then have a vector of t values, and we have our vector solution of y values.